This is the tepid coder. Everything is a number. When you type text, each of these have numerical values, each of those characters. You can see that if you go into character map in the Windows Start menu. Everything has a value. You can see down here the character code. 0x is letting you know that it's in hexadecimal, but each of these have a value. This is why if you open up something that's binary into Notepad, for example, you'll have some of these weird characters that aren't typically used. So I'm going to open a program here in Notepad. You can see there's a bunch of garbage characters. We could find each of these in the character map if we wanted, but some of the characters aren't going to be displayed because this only has a range of, what is it, 0x21 through 0xff, which is, I guess, plenty on the high end. The low end is missing everything from 0 to 0x21. So what you can do is you can take this into a hex editor. Now, I've made one. This is the hex editor that I've actually dumped into the Notepad. You can see what these actual byte values are. So let's do that. I peek from 0 to the first 1,000 bytes. You can see these are the actual byte values of every byte in the file, every character you saw in Notepad there. Now, part of what you see in an executable file is a header that the operating system uses in order to figure out how to load the code and use it. Windows uses something called the portable executable file format. That's what's going to be in this header. And on different varieties of Linux, you'll have the ELF format. Anyway, past that, you're going to have things like all of the strings in your code. You're going to have things like your actual code itself that executes, initial values for variables, that sort of thing. And if I keep peeking further into the file, 1,000 bytes at a time, we can probably find some of those strings in here if I went far enough. Might take a while. But that's not a very interesting way to do it. I think that simply going into the Notepad again like I had it will be more efficient. You can actually see right here there's a string. If I go further down, there'll be things that I wrote in the program, like right here. A bunch of potential errors that can come up when you're trying to do things. So all that's stored inside of the executable as well. But keep in mind, even this, if you go back to the character map, even these have values. I see a capital N right here, you know, that could be right here. It's 0x4e. And if you don't know hexadecimal, it's basically base 16 instead of base 10. So you can imagine counting from 0 to 9 is 10 values. And then past that, it's A through F. So A is 10, B is 11, C is 12, so on. F would be 15. And once you reach F, when you go to the next number, it'd be 1, 0. Kind of like when you go to 9, once you hit 10, you add a new digit and you replace the digit you were just on with a 0. So that's all it is. 0 to 9 and add A through F. So if you had the value like 1F, for example, it would be 1 times 16 plus 15. It's 1F. Because the 1 is being multiplied by the 16th place. You can imagine, I want to clear this out for a second. You have like, say you have the value 10 in decimal. It's basically saying you have 1 10 and you have 0 1s. Another way to look at it is you have 10 to the power of 1 times 1 plus 10 to the power of, oops, damn it, 0 times 0, right? 10 is that. And if it was like, I don't know, 210, you'd see I have 2 times 10 to the power of 2 in this case, plus 10 to the power of 1 times 1, plus 10 to the power of 0 times 0. And you keep doing it that way. Every single time the power of 10 goes up. But in this case, we're doing 16, so it's like 16 to the power of 0 times any number. It could be 0 through F, right? And then that's being added to 16 to the power of 1 times that, and then so on and so forth. You can keep making it bigger and bigger. CB2, CB3, dot, dot, dot. So that's all it is. Anyway, there's other things that are stored as numbers as well. Everything's basically a number in a computer. So if I go to Paint, for example, That's blindingly bright. Okay. If I imagine I pick a color, any color I want, you can see there's a red, green, and blue value. Each one has a range from 0 to 255. That's because each one is 1 byte. Typically in memory, there is red, green, blue, and alpha. The alpha isn't adjustable here because it doesn't really matter. There's no multiple layers of stuff being blended together. And 1 byte, the reason it has the range from 0 to 255 is a byte has 8 bits. Each bit can either be on or off, right? So you have 0 or you have 1, right? For each of the bits. And you can do that across 8 different bits. So, 0, 0, 0, 0, 0, 0, 0, 0, and you have 0, 0, 0, 0, 0, 0, 0, 1, dot, 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 dot. And eventually you'll get up to 1, 1, 1, 1, 1, 1, 1, 1, right? That'll be 255. All zeros is just going to be 0. In general, you can tell how many values you can store by looking at the number of bits you have and raising that to the... Sorry. You raise 2 to the power of the number of bits you have. So if you have 2 to the 8, that would be 256. But that's how many values you can actually represent. 0 has to be one of those values. So because 0 is one of those values, you actually have 1 less than this as the max value. So it'd be 0 to 256 minus 1. 56 minus 1, which is going to be 255, right? And that holds in general. So if I had, I don't know, 32 bits, it would be 2 to the power of 32 and minus 1. This is if it's unsigned, right? What the max value could be, 0 to that number, whatever this whole thing is. Now, if it's signed, you could basically take all of this and divide it by 2, right? And that would be the max negative value you could have. The max positive value you could have would be this over 2 minus 1. So all of this minus 1. That's the max positive value you can have. The reason for that is, you can imagine you'd probably have the same number of negative values and positive values, except we have a 0 in the middle. So if we want the value 0, we have to favor one side. Either we have more negative values or we have more positive values. The way it was chosen is that we have more negative values by 1. So for 8 bits, if it's signed, we can have up to, let's say, 2 to the 8 over 2 is your max negative. So negative this, up to, positive, it's going to be 2 to the 8 over 2, then minus 1. So what we're going to have is negative 128 up to 127. That's your range. And that holds true in general for any number of bits. Okay, so you imagine we have 1 byte per color channel, which is red, green, and blue RGB, and also for alpha, right? Each of these is 1 byte, which means each has 8 bits, which means each ranges from 0 to 255. You could make it range from negative 128 to positive 127 if you want it to be signed, but no one does that. So that's how that works. Obviously, I showed you each of the characters has its own value that it uses. When you're programming, all of those things have values too. So the code that you write actually ends up having binary values, just like this. I mean, obviously it does. I just showed you in hex editor. But if you go to godbolt.org, you can actually see the types of assembly instructions that are generated as you do C code. So I do something like, I don't know, let's say int square. This is the example that it usually comes with. So int x. We're going to return x times x, right? This is actually going to generate some code. Generate these assembly opcodes. I chose 32-bit because I have something that I wrote that uses a FASM compiler, which is a 32-bit compiler, and it shows the actual byte values of the assembly instructions that are generated. So if I wanted to, I could actually take these, and I could put it into my program, and find out exactly what the values would be. So let's do that real quick. So what do we have here? We have push EBP. We have move EBP ESP. We have move EAX to keyword pointer. I don't have that value. I'm just going to put some garbage in here because I don't actually have that defined anywhere. I'm just going to say, 131. Okay, imul EAX by keyword pointer to, let's just do 131 again. We'll do pop EBP if I can type. Return 0. Okay. That is the actual array of hexadecimal values. Each of these 2 represent 1 byte for that code. When you write this code, these are the actual values you get on an x86 instruction set. And to show you this actually works, I'm actually going to rerun this, and I'm going to write some code out here. So I'll write an actual program. We're going to do use32, because using Windows 32 API. I'm going to move AL to byte, SE string, which I'm going to define later. I'm going to add AL, 1. So whatever the first byte of the string is what I put into AL. I'm going to add 1 to that byte. So whatever I'm printing out, the first character is going to be 1 higher in the character set. So I'm going to go back to that character map for a second. And the string I'm going to make is going to be, this is like only a test. But I'm going to actually purposely put it in wrong. I'm going to say sys is only a test with an S. So if you look, 0x53 is that character. But the next one that comes up is 0x54 for T. So I'm going to correct that by adding 1 to it. And then I'm going to store that back in the string. So the way I do that is I say move SE string, AL. So I pull it out, put it in the register, AL. What's the lower byte of EAX register? It's the least significant byte. Then I add 1 to it, then I put it back into the string variable, or the memory address of that. That's why it's in brackets. Okay. So next what I'm going to do is I'm going to call a function which has a function declaration which is std call in C. This is a FASM macro that you can use. So makes my life easier. Instead of pushing things and having to worry about popping properly, it's going to do that for me. So I'm going to standard call message box. This is my own wrapper around message box A. Around that function which takes hwind, it takes const character pointer, const character pointer. It's probably actually a tchar, but that basically becomes const char, or it becomes const w char t. Okay, and at the end it has like an integer, or you can do like mb okay, or you can do like mb icon exclamation, those kind of things. Anyway, I wrap that around so I can call it easily in this. So I'm doing 0 for the window handle. I'm going to do a string. The string is going to be SE string, which I haven't defined yet. The same one over here that I was mentioning. Okay, then I'm going to do a string that I call on the fly. Testing, let's say 0, so it ends with a null terminator, and then 0 for the type, which is just going to be like an OK box. Okay, that looks right. We're going to do... Actually, I'll just return here, I think. Then I'm going to define my string. So SE string is going to be define byte. Say sys is only a test. Period. We're going to end it with 0. Anything else I need to think about there? No, it's in a message box. Should be fine. In the program there. So there's the code that I generated. And what I'm doing is I'm sticking the code generated, actual byte values, into a buffer. I'm flagging it as being executable. I'm casting that block of memory as a function pointer and storing that function pointer in a variable, and then I'm calling it. So I'm going to execute that code. We'll see if it works. There it is. Testing. This is only a test. You can see this is only a test, even though right here I wrote this is only a test, because I took the first byte out, I added 1 to it, and then I put it back in. And because of the way it's defined in the character map, that's what's happening. It's 1 higher, right? Thankfully, it's alphabetically ordered that way, so I can do that easily. But yeah, everything's a number. That's basically what I wanted to say in this video. All that really matters is how you're interpreting that number. If I wanted to, I could say something like, I don't know, this is an integer here, but I could really also pass an unsigned integer. I could multiply it and return it as a signed integer. It's going to be pretty much the same byte representation in memory. It'll actually let me do that. Internally in the compiler, it'll do like typecasting to make it so it converts between those types. But really, it's just the way it interprets those types in memory. I'm trying to think of an easy way to explain that. Here's what I'm going to do. I'm going to make a file called test3. I'm going to do stdio, so I can print to the console. I don't really need to use any arguments here. So what I'm going to do here is I'm going to say, how about, you know what, I'm going to include standard int.h. I'm going to make a uint8t, which is an unsigned 8-bit integer, right? And what I'm going to do is I'm going to say for, let's just do an integer, I equals 0, I less than 256, I plus plus. Now, keep in mind here that an 8-bit integer can be anywhere from the range 0 to 255. But what I'm going to do is I'm going to print up all the values up to 255. So it should show 0 to 255. That should work. Okay, so I'm going to do printf. Actually, I'll do fprintf to send it out. I'm going to do unsigned triu8, which is a format specifier for an unsigned 8-bit integer. And for that, I actually need type setH. Okay. And a line break, and I'm going to actually pass the value ui8i. And then ui8i plus plus. I'm going to increment the next value. We're starting at 0, just like this counter variable, and we're going to keep incrementing it. So I'm going to actually compile that. test3.cp, oh, test3, okay, test3. So it shows all the values from 0 to 255. But now what I want to do is I want to treat this differently. I'm still going to use an unsigned 8-bit integer for the storage medium, but I'm going to pretend like this is just a signed 8-bit integer instead of unsigned. Let's recompile it. We'll run it. That's a little bit surprising. That should actually be printed out as being signed. That's what this format specifier should be doing. So I think there's some shenanigans going here. I think what's happening is this is probably promoting it to a different storage class type that's slightly bigger when it passes the function, like an integer. It's like probably type punning happening. So, trying to think of a way I can avoid the type punning. I'm just going to do this. A static cast int 8t. I'm going to treat this unsigned value as being a signed value. There we go. So the same value, 0 to 255, you can see can also be represented with a range that has negative values. And like I showed, the max value, or max negative value, so the minimum value, is negative 128. The most positive value you can have is 127. And the way it's stored in memory is it goes from 0 up to the max positive value, then it kind of, what did I say, overflows into the max negative value, and from there it gets increasingly positive, or what did I say, increasingly, decreasingly negative, so closer to being positive. So, yeah, it turns out, like, when you have the bits all set, what you'd think would be the highest value actually ends up being -1. And if you wanted to count back from -1, you kind of, like, what do I say? It's almost like you're adding to it one at a time, but you're subtracting. By subtracting from -1, you're growing more negative. I'd have to show it in binary, which I can do that real quick. It's hard to explain, but I think it'll make sense if I just show it. So I'm going to do this, like, print byte, I'll call it. It's not going to return anything. It's, actually, I need to actually pass something to it, so. Byte, so I'm going to say for int I equals 0, actually, you know what? Do it the way around. I'll say it equals 7 greater than equal to 0, minus minus. Like, it doesn't even need to be this large. It could be, yeah, assigned 8-bit integer. So I'm just going to say something like fprintf, just the out, and we're going to say something like, I'll do unsigned c, and let's see, ui8 x, and 1 shifted left to the I. So if that current bit is set, then what I'm going to do is I'm going to say 1, otherwise we're going to put the character 0. Yeah. And we're starting from the right to the left. Making sure that's right, because when we print it out, we want to make it so that the right order happens. So let's say we have 0, 0, 0, 0, 0, 0, 0. I want to print out. Yeah, that should work. Because I want to print it right to left. If I print left to right, what's going to happen is, imagine you have this, like the least significant byte is, or bit right here. Let's pretend that we have like not a base 2, but like a base 10 or something. So you can have value 1, then 0, 1, 2, 3, right? And then the next 4 bits with air quotes would be like 4, 5, 6, 7. If I actually printed it out by checking the bits from least to most significant, it would actually write it out like this. It's like 0, 1, 2, 3, 4, 5, 6, 7. What I actually want to do is I want to read it from highest to lowest, and I want to print it out like this. It'd be 7, 6, 5, 4, 3, 2, 1, 0, right? That's what I'm doing here. That's why I'm starting at 7, and I'm stopping after I hit 0. Once it starts going negative, I'm going to stop. Okay, so after each of these, I'm going to say print byte I. And then what I'm going to do at the end here is actually give a line break. So I can kind of break that up a little bit and see what I'm doing. Okay. So like I was saying, all the bits are set for -1. And it's almost like you're adding, but in reverse. If you imagine adding in binary. And it kind of counts up, but it's becoming less negative. That's one way to look at it. So if you wanted to start at the most negative number and like imagine counting up by like the reverse operation where like you're counting with 0 instead of 0 becoming 1, 1's becoming 0, and you're just kind of doing that and propagating it. It kind of does that until it reaches the max negative value, negative 128 here, and then suddenly you're at the max positive value and decreasing from there. So I don't know, it's just an interesting thing to think about. And you can kind of look at any of the memory this way. It's just the way you interpret the value. If I do something like having a, say a floating point number, so it can be a decimal. Let's say float f something equals 77.31 half. What I can also do is I can say something like, turn 0 here. Let's print byte. I'll do this. Unit 8t byte p equals and f something. I'm just going to complain about that, so I need to type past. So I'm treating this like this is a pointer to an unsigned 8-bit integer. And what I'm going to do here is I'm going to say, for I 0, I less than 4, I plus plus. I'm going to say for each of the bytes of this float value, in fact, I'll make it more explicit what I'm doing, because I know a float's 4 bytes long, but up into the size of the float, so 0, 1, 2, 3, and then hits 4, which is the size of the float, and it's going to stop. So for each of the bytes, I'm going to say print the byte out, and the byte is the address right here that I'm using. I'm going to say p plus plus. I'm going to go to the next byte of the float value each time and print out what the value of that byte is in binary. And there it is. So I'm even a floating point value. It's just these bits in memory. Everything is just a number. It's the way you interpret the number. If I wanted to interpret that as a, what do I say, like a integer, I could do that, and it's going to give me probably some weird value. And it's kind of interesting to think about, too. Like, so something the same size as a float, the float is 4 bytes, would be an unsigned 32-bit integer, for example. I could make it signed, but I'm just going to go with unsigned because I can. Why not? Just call it x. Say it equals... Actually, you know what? I'll show you two things. So, if I do this, equals f something, and I print it out, it's actually going to... This typecast here is going to try to truncate it and pick the closest integer value it can by truncating. So I'm going to do %sign PRIU32, so unsigned 32-bit integer. And it's called 32x. Okay, 77. And the reason 77, like I said, is because it's actually truncating that value from 77.31. It just removes the decimal component, so it becomes 77.0, which is just 77. Okay, but what if I do something different here? I'm actually going to define this, but then I'm going to copy the bytes into it. So memcopy into the address of this variable. I don't have to do any typecast or anything because it takes a void pointer, and then over here it takes a const void pointer, right? Anyway, I'm going to copy it from f something, size of float, which is just 4 bytes, but I'll just say size of float or size of t, right? And then I'm going to print it out, and this is going to give me a different value, because I'm not converting the actual representation by truncating it and typecasting and all that. Oops, what did I do? It doesn't know memcopy, probably because it wants string.h for memgw, so let's do that. I think if I used Microsoft Visual Studio, it'd be something like Windows.h should have it. Oops, test 3. So yeah, this time it gave me a very different value, because this binary representation, as interpreted by an unsigned integer, 32 bits, is very different than it being typecasted into a 32-bit unsigned integer from a float by using some truncation and some kind of like opcodes. I'm not even sure what the opcodes would be to do that conversion. Let's see. We can actually find out over here. So if I do float f, let's call it equals 77.31, and we'll say like, all right, here. Dang it, I can't type. std_int.h. Let's say we have an integer, call it x equals int f. So what does it actually do to convert that? Is it not happy? Does not like unsigned 32-bit integers? I'm just going to say int then and assume it knows what I mean. It's still going to complain, right? Because they typecast int. Oh, because I haven't actually returned int. Let's return 0. Probably would have been fine then. Really, what is going on here? Okay, here we go. So it's doing this, convert CVT, so convert TS S2SI. Let's look at that opcode. Convert with truncation, scalar single precision floating point value to integer. So that's what's happening, it's converting it, versus just copying the bytes over, like I did in my little test program here. I just copy the actual binary data straight to a variable that's interpreted differently. Anyway, I think that's about all I wanted to cover for now, like everything being a number in memory, whether it's code, whether it's textual characters you see, whether it's a value you're working with, whether it's code itself, colors, whatever. And this is why it's important, by the way, to know what kind of data type you're working with. If I do something like, for example, say I'm parsing from file, or maybe I take some user input from the console, and I say like, okay, I have character buffer, let's say it's just called buff, it's got 256 bytes, you slice it to 0, you're doing something like fgets, whatever. You grab some crap, you put it in the buffer. What you're actually going to get here, if someone types like number 15, is you're getting like a const char buffer, it has like this value right here. It's the ASCII values, or whatever symbol set you're in, but character map here, just real quick. Gave you a 15, it would be 1 byte that has this value, 0x31, which is 3 times 16 plus 1, and then the 5 right here, which is 3 times 16 plus 5. So you're getting those two values. So you actually have to do conversions like, int I equals ATOI, which is ASCII to integer of buff here, right? Then it turns it into an actual number you can use. It would have the binary representation of this number. So what would that even be? You can imagine like 15 is just 0xf. F means all the bits are set. You can say 0f right there. And that would be like 000, and then the lower 4 bits would all be set, 1111, right? If it goes from 0 to f, being 15, then the highest one it could be must be that all are set. So that's what it would be in binary. So it converts this, which in the character map I told you those values were, into this. So that's where I'm going to stop it for today. Everyone have a nice day. Catch you later.